Welcome. Today we are looking at a function proof where we're going to look at the images of some function. I took this from the Discrete Mathematics and its Applications book, the 7th edition by Kenneth Rosen. This problem comes from chapter 2.3, question number 40. Now this is a pretty ubiquitous question, so you would find this in analysis, maybe abstract algebra, definitely an introduction to topology book. Any number of places in mathematics, you'll find something like this. So it's not particular to discrete mathematics. That just happened where I got the question from. So it's asking us that if f is a function from the set A to the set B, and then S and T are subsets of A, that f of S union T is equal to f of S union f of T. And then the second proof, we're going to show that f of S intersect T is a subset of f of S and intersect f of T. Now these are sets, S and T and A and B. We made a video about set operations. So if you need a review of set operations, you should look at that video, which I'll link above here. That goes over set operations, union, intersection, difference, complements, and other identities that you might need, what it means to be a set, what it means to be an element of a set, what it means to be a subset, what it means to be a proper subset, the empty set, and all those concepts you can find in that video. It's about an hour long. It's indexed, it's chaptered, so you can skip around if you need to. So I won't go into too much detail about those things since that video exists. So look for that if you need a review. So before we start with A and B, before we start the proofs, let's look at these functions a little, or this function a little. This is abstract. We're not going to define the function in any particular way. We're just going to say that f goes from A to B. And then we have the set S is a subset of A, and the set T is a subset of A. So we can draw a little diagram here of what this looks like. So let's say this is set A, and this is the set B. So the function takes elements from A. A is the domain, and then B is the codomain. And the set S, I'll put here, and set T, that means that f of S exists as a subset of B. I'll put that here. And f of T exists as a subset of set B. These are the images. Now, f goes from here to here, of course. So it takes elements from A to B. I drew the S and T as an intersection, and f of S and f of T as an intersection, but it doesn't necessarily have to intersect. So we could look maybe at an example where this is true at the end, but my diagram's just for illustration. It's not every case. It's not every case of S and T is going to intersect. So let's add that up here. Note that f of S is a subset of B, and f of T is a subset of B. So that's a setup. That's a situation we have here. We might want to define a couple things really quick, just so we can proceed. Again, these are in the set operations video. So this is just a quick definition of what a union is. So if A union B, this will be all X such that X is in A or X is in B. An intersection, this A intersect B will be all of the X's that X is in A and X is in B. So you can see the union requires it just the element to be in one of the two sets, whereas the intersection requires it the element to share between both sets. So these are important definitions for our proof. And let's maybe do the function definition here just to be thorough before we start. So I'll use our case. We have a function f from a to b. This takes elements x and maps them to f of x. Now, the function means that for each x in a, each x has exactly one output, which we'll call f of x in b. So those are the three definitions we'll need. I go into more detail about unions and intersections and other set operations in that set operations video, which you can, again, find in the description or above. So the first proof, part A, is asking us to prove that the set, these are sets now, f of s union t is equal to the set f of s union with the set f of t. So this is our first task, is to prove that these two sets are equal. Now, to prove set equality, we need to show this as two directions. We need to show that first, that f of s union t is a subset of f of s union f of t. And then second, so this is, let's think of it as directional containment this way. And then the second is that we will have to show that this is a subset of this. And we should think of this as that containment the other directions. So in set equality proofs, this is generally how we do it. We have to show that the one set is contained in the other and flip them around and do the same thing. Now, it's going to turn out, in most cases with an introductory text like this, that both directions will work forward and backward, meaning once I write out the first, say this, that if I wrote the proof from the end to the beginning, that I would get the same argument. Not the same argument, but the second part of the proof. I will write both directions out just as an illustrative fact so that if you are trying to prove this, it'll be more clear that way. Sometimes I just use bidirectional arrows that will allow me to say, well, if this, then this, if and only this, if this, if and only this, I will be doing that. So here's our proof. And then again, this is the containment this direction. And so with any set containment proof, we're going to establish an element in one of the sets. So we're going to let y be the element that exists in the set of f s union t, which is the image of f of s union t. So this is an image. And again, look at the set operations video. We talk about images and pre-images. So what do we want? We want to show here that y is in f of s union f of t. If we do that, then we've shown that every element, because y is arbitrary, that exists in f of s union t will also be in f of s union f of t, which is the definition of subset. So this is where we want to end up. Okay. So we have some element y in f of s union t. This will imply that y equals f of x because this is an image under a function. Remember our definition of function. So this is true for some x in S union T. In other words, I have this situation. I have a f of S union T, and that's here, let's say, and I have some element y. Because it's in the image, I know there's some element x, such that the function takes it to here. So we know that under the function, this is true. Now, you don't have to write this diagram in your proof. In fact, I would suggest you do not. That's just a sort of idea of what's happening. So the argument here is that y equals f of x because f is a function. So x exists in S union T. So then by the definition of union, x is in S and x is in T. That's what it means to be the union. So we have these elements x and s and x and t, two different sets. Now under the function f, because s and t are in the domain, all elements will have a map. So if x exists in S, that means that f of x exists in f of s. And it's also true that if x exists in T, which is again the domain, that we'll have f of x in f of t, the image. So this is true by the definition of f, the function. So now by the definition of a union again, if I have f of x is in f of s, I should be or statements, not and statements. My fault. There should be or. I'm using intersection. This is actually union. These are or statements. So by the definition of union, f of x is in f of s or f of t, which means that f of x is in f of x or f of s union s f of t. And since f of x is the same as y, as we said above, that means that y is in f of s union f of t. And that's what we wanted. We wanted to say that y is there. Now, since y is arbitrary, meaning it's not a particular element, we can conclude that f of s union t is a subset of f of s union f of t. So that completes that direction. And again, what I'm about to do is going to be this. If I took the above argument and I started here and then moved backward, we will get the other direction. But let me write it out. So this is this direction. So we're going to assume an element exists in the intersection, or the union of these two images, and then move the other way. All right, so this implies, by the definition of union, that y is in f of s or y is in f of t. So since f is a function, and y exists in the image of f of s and the image f of t, we know that y equals f of x in f of s for some x in s, just by definition. And again, the same is true for the other, that y equals f of x is an element of f of t for some x in t. So what does that mean? Well, that means that x is in S union t, since this is an OR statement. Now, under the function f again, we're taking elements of x in the domain, and S union t is a subset of the domain. So note that S union t is a subset of A. This then implies that f of x is an element of f S union t. So that concludes then that f of s union f of t is a subset of f of s union t. Now you notice again, this is the same direction, or sorry, the same argument of the above direction that starts at the end and moves to the beginning. Then since we have two subsets, we can conclude, therefore, that f of s union t is equal to f of s union f of t. Because they are both subsets of each other, by definition, that means they are the union. So that concludes the proof of part A. Fairly straightforward. Once you understand the definition of the union and the function, and what an image and domain and codomain are. So let's look at part B. Part B, our task is to show that the f of s intersect t is a subset of f of s intersect f of t. So you notice here that we don't have equality. We're just showing that one is a subset of the other. And we'll talk at the end a little bit why that's true. So this is our task. And again, when we are showing set containment, we're going to suppose an element exists and then show that it exists in the other. So in other words, we're going to, this was a proof. Let me write that better. We're going to suppose an element exists in f of s. Now you could skip this part by just saying that I have some f of x in, but I like this way. I think it's more clear. And we want to show that y is an f of s intersect f of t. This will be our goal. This is what we want to have happen. Once we've done that, then we've shown that set containment of f s intersect t is a subset of f of s intersect f of t. Okay, so now we suppose that y is in f of s union, no, intersect. I keep switching those. Forgive me here. These are not unions, these are intersections. All right. I'll try to remember not to write that. Now, since f is a function, and we are in the image, there's a y equal to f of x for some x in s intersect t. Now, by the definition of intersection, that means that x is an element of s and x is an element of t. So again, the definition of intersection is an and statement, union's an or statement, which I screwed up in the first side. Happens. Apologize. I think you'll get over it. All right. So again, f is a function. X and S and x and t are in the domain, so I am guaranteed that I'm going to have an f of x in S and an f of x in f of S, not S, and f of t. If we didn't, if there was no such f of x, then f wouldn't even be a function. That means that there will be some element x in S that didn't have a mapping, and that means that f would not be a function. So by the definition of a function, these have to exist. So f of x is in f of x and f of t. So by the definition of intersection, remember intersection says it has to be in both for it to be in the intersection. So f of x is in f of S intersect f of t. And that's what we wanted because we said that y equals f of x. So y is in f of S intersect f of t. Therefore, f of S intersect t is indeed a subset of f of S intersect f of t. We are done. So that's the proof of that direction. Or sorry, the proof of this part B. We don't need to show the other direction because this is not assumed to be equality. So as a side note, what would we need for equality of the second proof? We would need f to be injective. If f is injective, then equality would hold. And injective means one-to-one. So if we had a one-to-one function, the equality of part B would be true. But since it's not assumed to be, that means that we can only show that f of S intersect t is a subset of f of S intersect f of t. Here's an example of why. Let's say that I have a function f, and it's going to go from the elements 1 to into 0. So that's the entire image or domain, and codomain is 1 and 2 and 0. So this is a constant function. That means that f of x is always equal to 0. So let's say that S is the set that has 1, and T is the set that has 2. So what that means is that f of f1 is equal to 0, and f of f2 is equal to 0. Okay, so what is f of S intersect T? In other words, if I take S and T and intersect them, and then look at what's in the image, we'll notice that, well, the intersection of S and T is empty. So it's empty. There's nothing in this image. However, if we look at f of S intersect f of t, f of S takes all the elements in S, which is just 1, and puts them to 0. So that is the same as 0 intersect, and t does the same thing. So this is 0. And of course, the empty set is not the same as the set that has 0 in it. So this is why we don't assume equality. I found a counterexample if we did assume, and you can see quite easily that this is not a one-to-one function. It's surjective, but it's not injective. So that concludes this video. Please like and subscribe if you need some set help. Again, look at the set operations, properties, and identities video. And let us know in the comments if there's some set proofs that you would like to see or something I'm not covering. We'd love to hear from you. We appreciate it. You have a great day.